Hi everyone. In the previous lectures, we have we have come across and we have studied calculus. We have studied multivariate functions. We have studied the derivatives, especially the gradient and the Hessian. We have come across matrix derivatives as well. So we have an understanding of some of the calculus that is involved. In today's lecture, what we are going to look at is what does learning mean when we are studying machine learning algorithms? What does learning mean? So, as Professor Arulan sir has already mentioned in all the previous lectures, that calculus forms one of the foundational pillars of learning of understanding machine learning algorithms and AI systems. Today we are going to look at one of the reasons as to one of the reasons for the same a little more deeply. So firstly, learning is in fact, as has already been discussed, it is in fact minimizing a cost function. So, in today's lecture, what we are going to do is look at what this minimization exactly looks like computationally. So that is going to be the crux of today's lecture. So to begin with this entire process, it starts with looking at what cost functions are. So you have already looked at, you have studied and come across what optimization is, unconstrained, constrained optimization in previous lectures. So you would have come across what is cost function. So cost function is what you want to reduce, and then and this process of reducing the cost function with respect to certain parameters is what is known as fitting of the model into the data, or that the model is learning from the data. So let us denote the cost function. So let's begin there. So let us denote the cost function as E of omega, where omega is the set of weights or parameters from the model that you are actually trying to fit into the data. So yeah, it could be a supervised learning model, it could be an unsupervised learning model as well, wherein you form or frame this cost function slightly differently. So whatever be the machine learning model that you're trying to fit, at the end of the day, you are trying to minimize a particular cost function and then trying to fit the data. So let's denote it as E of omega. So let us understand mathematically what are the properties of this E of omega. So omega is like set of weights or parameters, right? So omega is also a vector. So you have studied linear algebra already. Now you have come across linear algebra, and omega will be a vector, especially when the model that you are trying to fit has some n number of parameters. Like if you look at neural networks run into millions of parameters, in fact. So when you have models like that, you have omega being a vector which belongs to some Rn. So omega belongs to Rn. So looking at the properties of the cost function, so you can clearly see the cost function is scalar valued and multivariate. In fact, we can make this more concrete for us to think about the properties. So let me take an example. Okay, so supposing we have a training data. We have, let's say, some training data xi ti. So what I'm imagining right now is a regression problem. So ti is the target variables, xi is the feature variables on which the target variable is dependent upon, and we have n points, capital N points. So supposing if this is our training data and this is a regression problem that we are looking at, and then if we look at, so you have come across least square cost function as well. So if we look at the least square regression problem for some model of regression, let's say f of omega comma xi, this is our predicted variable yi. So if you look at this model and we are looking at the least squares cost function, so E of omega xi would look like summation I is equal to 1 to n yi minus ti square, right? This is the least squares cost function. So the cost function E is dependent on the parameters as well as the training data. So that is our point number 2. When we are looking at the cost function, point number 2, it includes training data as well. So this is computation. This is something which is important computationally, as we will know throughout the lectures on gradient descent. So the other thing that we want to look at about this function is that generally how we are building models, these models are going to be such that the cost function turns out to be a continuous and differentiable function and differentiable twice. This is a multivariate scalar valued function, right? That is point number 1. This is also going to be having at least 2 derivatives. So the first derivative, which is the gradient nabla E. So this is our assumption right now for this lecture, but even in practice you are choosing models in such a way, most of the time you are choosing models in such a way that the gradient exists and then the Hessian also exists, which is the second order derivative. So nabla E exists as well as the Hessian. So I will denote the Hessian as H exists. Okay, so these are 3 very important properties of the cost function that we want to keep in mind when we are arriving at the gradient descent algorithm. So the way we are working today is how to arrive at the gradient descent algorithm computationally. I mean, at the end of the day we are trying to make it work on a system, on a computer, which is all discrete in nature. So we will keep that in mind. Yeah, so there is one more thing that we want to look at here when we look at the cost function. So when we come back to this, and supposing this parametric model was a linear model. So this again you have already seen in previous lectures. If this was a linear model, our cost function would have a single minima, the least squares cost function, which would be the global minima, and then we would arrive, whatever we do, we have only one minima that we want to find, and then that minima would be the best fit of our model into the data. But it can also happen, so let me just make this clear. If linear model, then one minima. If not, it could be a very complex model, it could be a hierarchical model. So what do we mean by hierarchical model? So when we say hierarchical model, what does it look like? So f of omega comma xi could actually be, so I will just write hierarchical model here. So f of omega xi could actually look like some function g, eta is again parameters, comma zi, where zi is actually again coming from a different model, which is h of theta comma xi. So this is like 2 levels of hierarchy here if you look at it. So omega would actually be combination of both this theta vector and eta vector. So omega would be a conjoined vector of theta as well as values in theta as well as values in n. So this would be a vector over which you would be trying to optimize the cost function. This would be the vector space, and this would be one particular vector corresponding to that parameter. So this is an example of a hierarchical model. So many, in fact, there's the most famous hierarchical model that is used everywhere across industry problems, across academic problems, and so on, and that is the neural network, right? Every layer actually corresponds to a nonlinear model, and every next layer is now a composition of all of the nonlinear functions or nonlinear models in the previous layers. So this is a very clear example of a hierarchical model. Example, neural network. So in such cases, what happens is that the cost function is going to not have a single global minima, but it is going to end up having a lot of local minimas. So and then in our challenge would be to find that particular minima, which, I mean, our ideal challenge would be to find that particular minima which minimizes the cost function entirely, which is the global minima. So that is a difficult problem computationally. So now that we understand and have some idea of the cost function, what we want to look at now is how do we find a minima, okay? And the answer to this is what are called as the one set of answers to this is what are called as the gradient descent algorithms. So let's start with what the theory explains, right? So from knowing of calculus, we know that given that there is a function which is differentiable, it has the gradient, it has the Hessian existing. What do we know? We know that if there is a minima, at the point of minima, gradient at the point of minima the gradient there, let's say the minima occurs at omega hat. So the gradient at omega hat is going to be 0. This is something that we know from theory, we know from our study of calculus. And what happens and how do we know this is a minima? So because the gradient is going to be 0 at minima, at saddle points, it's also going to be 0 at the maxima. So how do we know this is a minima? We look at the Hessian, right? So Hessian at omega hat, Hessian of E at omega hat. So I'll denote it this way. And if this is a positive definite matrix, right? If this is positive definite, then we know we are looking at a minimum, right? So this is what we know theoretically, but what happens in practice is that the function E might be a very difficult implicit function. To directly determine the value for omega hat, so find omega hat, the caveat would be, or the problem would be here, to express E of nabla E of omega hat, which is the gradient at omega hat. So you have the form of the function E, and then once you calculate what is del E going to look like, then writing del E of omega hat explicitly in terms of the other variables. So explicitly in terms of the other variables. So, meaning to write it as f, so omega hat is equal to some function f, might be very difficult to write. Okay, it might not even have an implicit form. So in such cases, we cannot solve for omega hat from this equation. So that is the beginning of all our computational troubles. So to arrive at this omega hat analytically would be very difficult. So and then the computer will not be able to calculate omega hat directly. So how do we go about this, and how do we come up with a workaround for this? So as has been explained in earlier lectures when we are actually looking at and studying calculus, what do we know about the gradient? So the gradient, the gradient is actually giving us the direction of the greatest increase of that function. So in the case of minimizing the cost function, what does that mean? It means it is giving us the direction of the greatest increase in the cost function, or the greatest increase in error of the model. So what is obvious? So supposing we are standing at some point in the parametric space, we don't want to go in the direction where the cost function is going to increase in value. In other words, the model is going to increase the error while it is being fit. The model prediction versus the actual, the error is going to be higher if we move that way. So we don't want to move in that direction at all. But what about the opposite direction? Obviously, that is where we definitely want to move, because if you are moving in the opposite direction, that means you are reducing cost function, that means you are reducing the error of the model. So we want to move in the opposite function or opposite direction, right? So supposing we start, so let's put that down in words. So supposing we are starting at some point, so we start at some point, let's say we are starting at a random point, because we don't know where we are starting, right? So might as well start anywhere. So we pick that point randomly. So start at a point omega hat. So that is what, this is the random initial point. So now once we start this, we have to now easily, like we want to know the direction of greatest decrease in error. Therefore, calculate the gradient nabla E at omega hat, right? So now we know the direction. So let's move in the opposite direction. So point number 3. So what is the next step? So omega 1. So actually let me denote this differently. Let's not use omega hat here, because we took omega hat to be a point of minima while discussing theoretically, purely theoretically. So let's call this as omega naught. It also means like the beginning 0. So E of nabla E of omega naught, the gradient, and then omega 1, the next step. So that was the 0th step. The next step, omega 1 omega naught minus nabla E of omega naught, meaning moving in the opposite direction. Okay. And then this is what happens. So this is what is done iteratively. So what you are also looking in parallel, you are also looking at the gradient nabla E of omega 1. Okay. So how do we, and then we do this iteratively. So we keep taking step, we keep moving. So omega 2 is going to be omega 1 minus del E of omega 1, and so on. So the ith step is going to look like omega tau, let me use omega tau plus 1 is equal to omega tau minus del E of nabla E of omega tau. In parallel, you are looking at nabla E of omega 2 here, nabla E of omega tau. Okay, so how do we know that we are arriving at the minima? That's what is on the top left end of the screen. The nabla E of omega hat is going to be 0, right? So we are looking at the sequence of nabla E of omega 1, nabla E of omega 2, and so on, and then is this limiting to 0? This is what we are looking at. So, once we arrive very close to 0 and we are happy with it, that is where we end, and that is going to be our omega hat or the minima that we have found. And we are going to evaluate E of omega hat to quantify the error of the model that we have arrived at. So, E of omega hat quantifies error of model f of omega hat. So, I can write it as omega hat comma xi. So, this procedure now helps us to arrive at the minima, right? Or does it really help us to arrive at the minima? There is something that we have not focused upon right now, and that is, there is an issue here that we have not focused upon, and that is nabla E of omega hat, nabla E of omega tau, right? Nabla E of omega tau might be very large in value, so that when you are at that tauth, when you are at that tauth iterative step, nabla E of omega tau might be so large in value. In fact, the step size or the step that you are going to take might completely overshoot the minima, and then you might not arrive at the minima at all. So, you might overshoot it, go to a portion of the space where the cost function has another increasing gradient, another high value gradient, again overshoot it, and then in fact it can diverge completely. As you can see in the visualization, that's a particular example where this actually overshoots and then diverges, and then you don't arrive at the minima at all. So, we do not want this to happen. We want to arrive at the minima robustly, right. So, we want to be able to come there. So, how do we work around this again? So, we want to work around this, and how do we work around this? So, if you I mean, we already have the answer. When we are analyzing and looking at nabla E, what did we mention? We said nabla E probably might be so large in value that it will overshoot the minima. So, how do we go about controlling that? The quickest way is, so let me just write the iterative step. Omega tau plus 1 is equal to omega tau minus nabla E of omega tau, right. So, we want to control the magnitude of del E, nabla E of omega tau, right. We want to control the magnitude, meaning what? Just add a scaling factor, and this scaling factor eta is called as the learning rate. So, now once this learning rate is introduced, as you can see in the visualization again, we have a controlled descent and we actually arrive at minima. So, choosing this learning rate would be very important, very interesting, and by choosing the right learning rate, we actually arrive at the minima, as you can see in the visualization. So, this entire procedure that we have come across, we have studied and looked at right now, is what is called as the gradient descent. So, let me write that in red. So, this is what is called the gradient descent algorithm in common parlance. So, in fact, this is the simplest form of the gradient descent algorithm, And why is it so simple? You will have a fair idea in the next lecture. So let me just summarize with what we have discussed so far in this entire lecture today. We saw that the learning in the learning in machine learning algorithms actually correspond to minimizing a cost function. We looked at what are the properties of the cost function, what it looks like, and what are the properties. I mean, we actually isolated and specifically looked at those properties that help us arrive at a computational algorithm to find a minima. And we actually made the correlation that finding the minima also implies that we have made a good model fit into the training data. And then we also looked at the iterative procedure. We looked in particular, we looked at the iterative step, which forms the core of the simplest gradient descent algorithm that we came across, which is omega tau plus 1 is equal to omega tau minus eta nabla e of omega tau. So this is the iterative step. So we also in particular focused on the fact that the cost function might have many minima, and we might land in a particular local minima, right. So because once nabla e converges to 0, now the iterative step is going to halt at a particular point. Omega tau plus 1 is going to be omega tau because the gradient there is 0, right. So we are going to be, what does this imply? This implies that you are going to be stuck at the local minima. But what is our idealistic point that we want to actually arrive at? We want to arrive at the global minima, right, which I mentioned at the beginning when we started working on this algorithm. So we looked at all of this in this particular lecture. What we are going to look at in the next lecture is we are going to look at this iterative step a little more deeply. We are going to look at it a little more abstractly as well, and then we are going to study algorithms, how we arrive at algorithms, how by tweaking this part we are going to arrive at algorithms like the stochastic gradient descent, or we also by reframing this iterative step we can actually arrive at what are called the Newton methods, and then what is the slight difference between Newton method and quasi-Newton method. So we are going to look at all of those things in the next lecture, and it is all dependent on how we look at this particular iterative step, which is omega tau plus 1 is equal to omega tau plus delta omega tau. So that is the step size. So how do we take a step is going to lead to different kinds of gradient descent algorithms, because we are using the derivatives, the gradient and the Hessian and so on. These are all called as the gradient descent algorithms. So we will look at that particularly in the next lecture. Thank you. See you in the next lecture.